Communicating now? There it is. Great, great, great. Okay, so the good news is that you guys are now incredibly well equipped to run computers and know computer science all the way down to the silicon. I could put you on a desert island, and if I gave you enough coconuts and twine, you could probably spend about a week and put together your first transistor. And then a week later, you could build your first AND gate. And then once you got your AND gate, you figured out how to build an inverter. And then you're off to the races. You can build a MIPS interpreter on your desert island with a whole bunch of coconuts and a whole bunch of free time. So, as we've been discussing, we now have covered what assembly is, what the stack and the heap are, what memory management looks like, what virtual memory management looks like, and even we did a mad dash for the last week here. We know I/O, so finally we can build these devices that communicate and interact with the outside world. So we're done, right? Better yet, because of some great interventions that we've had, some innovations here at Berkeley for the curriculum, we've also taught you how to parallelize these things. And so this class right here is going to be talking about, given everything that you've learned so far, you know how to make computers. You know how to make the best computers. You know how to make them go super fast. 60 gigaflops in your Project 3. The question, I got some laughs on that, yeah. Now that we know how to do things as fast as possible, it's time to let you off in the world to discover what you should do and how you should be implementing it. So you're about to leave the nice little intro nest of how to build a computer, how to code a computer, and you're going to start learning more and more about algorithms, more about the specifics of computers. And specifically about that, we have some news in computer science. Coming here, right on campus, Virginia Vasilevska-Williams is a postdoc here, dual appointment at Stanford, who came up with a convex optimization problem which treats its outcome, the objective that it's minimizing, as this exponent right here. And so she ran a solver long enough, given this genius formulation of the problem, to prove an upper bound on how long it takes to multiply any arbitrary n by n matrices. So you remember Project 3? Remember how you're trying to make it run faster and faster and faster? Right here on this campus, we now have a much better understanding of how fast it could ever possibly get. And it's on this scale. Before, we thought it was n to the 2.374, and now, fresh off the presses, we believe that it's actually n to the 2.3727. Which is amazing. This is a fundamental problem in computation. Doing matrix multiplications, doing them well, doing them fast, have all these limitations that we've been slowly chipping away at. So this, now that you know how to build a computer out of coconuts, now that you know Mosey, now that you know strides, now that you know page faults, now comes the time where we figure out how to do actually useful things with computers. And this is what that looks like. Doing that better and better is chipping away at this number. Boo, yay. Boo, yay. Right here on campus. So again, I'm Brian Gawald. I'm pleased to be here. I'm giving you a quick guest lecture today. The photo up there is also from campus. Steve Hanna, who's doing a great job co-teaching a course with Don Song this semester, is around. You should definitely look him up. Took that lovely photo. And to announce today's topic, we're going to be talking about Amdahl's law and the economics of parallelization. So as I said, we've taught you now not only how a computer works, but we've incorporated these great ideas from computer science to bring in how a parallel computer could work, how multi-threading is your friend. And the idea, the inspiration for this is pretty well summed up. Many hands, light work. If we can do simple things at the same time all at once, we have 20 people all working on one instruction. It only takes one instruction step to get 20 things done. That's a huge speed up. But it's hard. We had to worry about overhead for the threads. We had to worry about shared data. And we had to worry about caches and resources and bandwidth from our I/O devices, all being shared. But of course, you know exactly what all is going on with that. You're very well positioned now to optimize your stride and your caching to prevent things like false sharing or overloading any particular I/O channel. So, after you handle whatever synchronization you need to do, and after finding the right parallel algorithm that you need to do the task that you've been handed, and after finding a memory solution or any shared resource solution, all of these things now very familiar from your lab work, and after you figure out what to do in case things go pear-shaped, if a worker dies out, who's going to take over his job? That was Project 2 for us with Hadoop. Well, we're well positioned, right? With parallelization, which you guys are now equipped to understand and engineer, You can just add more and more and more workers, more cores, and chug them away on your project, and you'll just win. Right? Right. That's why there's a question mark after it. Let's take a quick look at an example here. Very simple. We have a destination vector and a source vector, both of them 100 elements long. So what we're going to do is we're going to step through each size here, and each element is going to move from X into Y. Very simple. And at the end of that, we're going to just print out, done. It's over. A simple message using that I/O device of the monitor. Maybe it's using memory mapped I/O to put D-O-N-E on some data word somewhere that can be read out by the OS and funneled off through a driver to the I/O device to print F, done. Very simple. So if we think about this, under a couple of assumptions, this takes about 110 instructions to run serially. So this is assuming some magical, mystical, handed down by the gods AMAT of one cycle. And similarly, we're assuming some magical, mystical, cost-free, zero-cycle comparator and increment for the actual for loop. So we talked a little in lab about how unrolling helps because it gets rid of those two steps. For now, we're just assuming away in this lecture that it costs us anything at all. We know how to make those cost less and less and less. So let's also assume that printf is also just given. It's 10 instructions written back in the 70s. It works. Don't mess with it. So if we set up a successful parallelization scheme, maybe with multi-threading, OMP, OpenMP is a good start. We could make each loop iteration run in parallel. You know, maybe we'll handle the false sharing appropriately. We make sure that all that's out of the way. We're really good at that now. If we could just run this in parallel, how fast could we make it run? So again, we're fixing our caching so there's no collisions, no mosey nonsense, and we're assuming that there's no overhead for each thread that we add. So we're assuming just the most well-behaved parallel system that we could possibly come up with. So if we look at this, in purple here we've got the loop, in blue we've got the old legacy code. So if we've got one core, 110 instructions. If we have two cores, then, well, we've got 100 things we have to copy over. So if each core takes half the work, then it takes 50 steps for each core to finish its part of loop duty, for a total of 10 instructions to do the printing, 60 instructions total. So with two cores, double the number of cores, we get a speed up of, well, if I divide 110 by 60, I've got 1.83. That's not right. It's very close to 2, but not quite so good. If we double it again, up to 4 cores, then we only need 25 instructions of real time to move through the loop. Still takes 10 instructions to do the old legacy code, though. Total speed up now, 3.14 instead of 4. If we go to 8, it takes 13 instructions, 12 and a half if we could have half an instruction done between different cores. Still, this printing from 1973 refuses to speed up. It's all going to be run on one core at once, talking to the I/O. Still takes 10 instructions, no matter how many cores we've added. Takes 23 total, that's 13 plus 10, for a speed up of only 4.78. And look at this, it gets even worse. When we doubled before from 1 to 2, 1.83. That's sublinear. 2 to 4, 1.71. That's even less sublinear. That's even sublinear. And then you can see that it gets worse and worse and worse. There's this marginal return from adding a core that diminishes the more that we have. And why is that? I think you know the culprit. It's this non-parallelizable print statement here. So here's just exactly what we were talking about, made graphical. If we imagine the amount of time that the program is spending in each part with one core, 100 instructions to do the copies, 10 instructions on the print. 2 cores, the purple part gets cut in half, the blue part stays the same. As we add more and more and more, the purple part gets lower and lower and lower. Our loop takes less and less time, but there's nothing we can do about the legacy serialized code. Which means, even in the limit, we know it's going to take at least one instruction set. If we have more than 100 cores, we can do all the processing in one step, one instruction. We're still going to have 11 instructions total to finish this code. Total speed up, well, it took 110 with one core, takes 11 now, biggest possible speed up that we're seeing, even with perfect parallelization, even with perfect unrolling, perfect moseying, perfect cache strides, everything, 10x. And that's with 100 cores. So they realized that this was coming in the 60s. I think it was 67, 68 thereabouts, where a Norwegian-American scientist named Gene Amdahl, still alive, by the way, still working, still making the rounds, published a paper that talked about this very problem. This idea that you've got diminishing returns because some of your code is parallelizable and some of it isn't. And what he proposed was this equation right here, where 1 over 1 minus p plus p over n gives you how much you can speed up your code with n cores. So if your code has a certain percentage of which can be parallelized, and you're using n cores to run it, you're looking at a speed up of f of n. So the logic here is no matter what happens, we've got this percentage which can't be parallelized, which is just sitting there eating up our cycles, eating up instructions. Nothing that can be done by adding another core to it. However, this one part, p here, the part that can be parallelized, gets less and less intense as we add more cores. So in the denominator here, you can think of the total number of instructions that we had to deal with. So sort of like this. As n gets bigger, 1 minus p plus p over n gets smaller as n goes up. Invert that to get a sense of what the speed up has been. You know, opposite of duration is rate. So what's the biggest rate we can get? Well, it depends on how parallelizable our code is. And more to the point, this is actually the dismal part of Amdahl's law, is the idea that if we had infinite cores, a gazillion of them, if we take n to go to infinity, and then p over n drops out, and we're left with the inclination that if we've only got 80% of our code parallelizable, then we're left with the maximum possible speed up of 1 minus 80%, or 1 over 20%, or 5x speed up. Best we can do. Amdahl's law. And we can see that the effects of this kick in pretty quickly. Here I've got a plot of just what this equation looks like for a series of cores. So this is number of cores on the x-axis, and this is percent speed up that we can get as a multiple of how fast it would run with just one core. So we've got a single program that we're trying to get to the end of, and we can throw a variable number of cores at it. So here on the red line is what happens if we've got 50% parallelization. If half our code is amenable to being split up a bunch of independent agents, independent actors, then we're looking at a very quick rise to an asymptote of what's the limit here? 1 over 1 minus 50 gives us 2. 1 over 0.5 gives us 2. 70 here, you can see that it's rising, heading for an asymptote of 1 over 0.3, or about 3.3x speed up. And this is after assuming you've done everything perfectly with your parallelization. You know, we saw before how we could have false sharing between multi-threaded applications. If we had 2 different threads fighting for the same cache block, that was bad. We had one of them arguing that I own it, no I own it, no I own it, no I own it, and they have to constantly fight for this shared resource. This is not that. This is saying, even if that were solved, if the code that we're running, if the algorithm that we're implementing is only amenable to p% parallelization, we have a very quick asymptote for how fast we could ever make it speed up. You can see that the concavity of this curve is actually fairly sharp. We hit the 90 percentile, 80 percentile range of the best we could ever possibly do under Amdahl's law very quickly. Very few cores, 8 cores. 70% percentile, you're very close to as fast as you could get with 1,000,000 cores. I mean, 8 cores, we've got that in the lab. And you think about what this means, because we talked about, and I like this lecture because it's kind of a review lecture. I get to go poke holes in all the other stuff that we talked about earlier in the season. We talked about that magical chart, that chart that we all love, the one that showed processor power going up, 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 and then flatlining. But it was okay because cores were going up, 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 up as of 2005. We hit that power wall, it was all right. We can just keep adding more cores. Here comes Amdahl's law saying, look, baby, 8 cores, you're done. You can't speed up past that anyways. You're doing incremental improvements past that. So some of the assumptions, this is Gene Amdahl. And Amdahl's law here makes a couple of assumptions. And in this sense, it's Amdahl's law in the sense that Murphy's law is a law. It's more of a guideline. Say's law is a law in a sense that it tends to obtain. So baked in, as we said, we're saying there's no contentions for shared resources here. The effect that we're seeing has nothing to do with fighting over who gets network traffic this time between our 8 threads. It has nothing to do with who's got ownership of this cache block, or, hey, what happened? That guy just knocked my page out of physical memory, and now I've got to wait for it. This isn't that problem. We're saying, he's saying, imagine it's already solved. So in the real world, it gets even worse. That's why it's in red there. The real world performance is going to be even slower than that. We're going to have to solve a problem in order to get up to the Amdahl optimum. He's also saying, let's assume there's no per thread overhead. Every time I add a thread, there's no setup costs, which we know to be false. If we have to make a call, for instance, to find your thread ID in your OpenMP, that's a bigger and bigger lookup with more and more threads. More overhead means more cycles for the OS to manage all of these threads, et cetera, et cetera. It's clearly not the case. So, in the real world, not only are we subject to Amdahl's law as a function of how parallelizable our algorithm is, we've also got the problem of fixing this. So we're not looking at a problem with overhead. We're looking at a fundamental problem with algorithm. And finally, well, here we catch a break. Amdahl's law says, let's also assume nothing's being pipelined. So what this is saying is that we're assuming that the serializable stuff all has to run at once, and then the stuff that can be run in parallel can be run. So Amdahl's law works really well for this diagram that we saw earlier. This was kind of the model that in the late 60s was being discussed. We've got some serial parts, the master thread, this is very familiar, forked into a whole bunch of parallelizable stuff. Here's where our M cores can really cut loose. Unfortunately, then we have a join, we go back to a serialization part. Now, a pipeline system may have something like, okay, we could do a serial thread parallel over here, and maybe that starts injecting data later in the stage. So maybe we could catch up. Maybe we could catch up a little bit, but frankly, we're still dealing with digging our way out of getting the perfect resource sharing and thread overhead mechanisms in place. So it's all kind of a wash. In general, Amdahl's law is a nice guideline to give you an idea of how good we can ever possibly get. And also, just for fun, Amdahl's law rounds off quantization. So if we go back a little bit, go back a couple of slides in your handout, you can see that this drops down and down and down and down and down, but we know that in the real world we're going to have to spend at least one instruction to do this, even if they're all done in parallel. And what Amdahl's law says is, okay, let's imagine, even more ideally, that this one instruction can itself be split up into tiny, 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 tiny pieces. If we have 1,000,000 cores, each of them gets 1/1,000,000th of that instruction. So for our analysis heretofore, going forward, we're going to talk about, let's imagine that this can actually be shrunk all the way down to 0 with appropriate parallelization. We can add enough threads in this that even below 1 instruction threshold we can get to. So that's the setup. That's the game that we're looking at here. Parallelization is an aspect of the code that we're running that we're going to have to consider when we talk about the systems that we build. So the systems that we've been building, when we've been building new systems, have been in the cloud. We've talked a lot about Project 2, another touchstone back into the earlier part of the course. We took our code and we decided we would parallelize it by just renting machinery in the cloud. And the idea was, okay, if we want to get twice the speed up, was the hope, we just go and grab 2 times as many nodes in our cluster. We can build a cluster with twice as many compute units, let's say. And of course, this just raised a whole bunch of resource sharing problems and a whole bunch of bottlenecks, because when you did your MapReduce, who got an actual 2x speed up by going from 3 to 6 on the Berkeley-Stanford web graph? Anybody get close? Anybody get 1.5? Anybody get 1.3? Yeah, there we go. We're looking at, these are the 1% in terms of speed up. I myself went from 16 minutes in iteration to 11 minutes in iteration. And that was a doubling. So the hope was, if we can go to a speed up of 2x by buying twice as many nodes in our cluster, the hope was we could get twice as much processing done. And why do we like that? Well, generally, you know, some of us are altruists, some of us are academics. But most of us in the computing world, we're doing this for a living, right? Like, if you're doing a business where you analyze somebody's Twitter stream and then tell them, I don't know, some other Twitter user that they are most compatible with, you're going to want to press through as many Twitter users as possible to set up in this little love connection that you've set up going. Maybe you get $1 for each time you run the match. So the more you can do in an hour, the better. And if you rent your computer for the entire hour, whether it's idle or not, the faster you can speed up your code, the more you can throw through there, the higher your revenue. That's good. So we've got a sense now where the faster we can make our code run, the better. Almost directly proportionally. If we get a 2x speed up, we can move twice as many customers through, we can get paid twice as much. Of course, we also have this linear scaling in costs. We have, thanks to the chronology of our births, access to these incredibly elastic cluster sizes. We can add cores to greater and greater extents. Maybe we have to engineer around networking and communication and resource sharing between those cores, but we can get arbitrarily many cores. And at this point, it comes X dollars for one core, K dollars times X for K cores. So that just scales up and up and up and up and up. And honestly, it's not as dire as it sounds as far as getting them to communicate, because with virtualization, when we say that you're buying one core, they're actually just time-sharing one incredibly fast processor with you. So it's actually not so bad virtualizing yourself all the way up to arbitrarily many cores. So resource sharing isn't going to necessarily cripple us. And of course, we've got this idea of different price points for the hardware that we're looking at. Do we want 1.2 gigahertz processor, or do we want 3 gigahertz processors? Do we want 1.7 gigabytes of RAM, or do we want 7 gigabytes of RAM? And all of this enters into our business decisions. You figure out what your algorithm's doing, how expensive it is in terms of memory use, how computationally intensive it is, and you find the right model for you. And if you want to scale it up, if you want to run your algorithm in parallel, just buy more of them, KX for K cores. And of course, all of this still holds for really reasonable grounded purposes if you built your own rig as well. I mean, if you rolled your own supercomputer, you'd still have to pay extra power costs for every processor you were running. So all of this intuition should guide us when we start thinking about what kind of system should we put together now that we know, and we got an inkling of this in Project 2, that we can't just go faster, 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 faster by adding more and more agent Smiths, replicating those cores all over the place. We've got a fundamental limit, according to Amdahl, on how fast we can go. So if we know that infinity isn't the answer for what's the desirable number of cores, let's start asking ourselves, what is a desirable number of cores? So here we go. Same plot that I had before. Amdahl's law. Very familiar curve to you now. Huge, huge ramp up here as we go from 0 to 1, because a speed up of adding one core compared to having no cores at all is phenomenal. But then you can see it immediately drops off. Going to 2 is not doubling. Going to 3, going to 4 is not doubling over 2. Very quickly hits an asymptote. Even if you're 90% parallelizable, you can see this bend here. So let's assume we lump in a proportional rate between how fast we can go and how much we're paying, such that this y-axis here is now some unitless comparator between how much we're paying and how much we're earning. If we get a higher speed up, that's good. We get more revenue. If we get more cores, not only do we get a higher speed up, we also get higher costs, however. The costs rise linearly, proportional to the number of cores that we're renting, or the number of cores we deign to put into our energy hog supercomputer. And then we've got a sublinear rise, an asymptotic rise in the payoff by adding more cores. So right off the bat, we know there's a limit. Infinity is no longer the answer. If I told you that you got $2 for running 27 cores, but you had to pay close to $2.50, no sale. 27 cores is right out. We can use this chart to say, okay, right here, for the red line, if I know my algorithm is only 50% parallelizable, no way for this cost am I going to want any more than 19 cores. Similarly, if I change my algorithm, speed it up a little bit, make it 70% parallelizable, still I know 31 cores, most I could ever possibly want. If costs exceed benefit, if the costs of adding more cores exceeds the benefit from speeding up by more cores, don't do that. You're losing money on every sale, and you will not make up for that in volume. You can see here we're in much better shape at 90%, but even this is going to hit a limit. And that limit's going to be much sooner than you'd think. You know, we talk about cutting-edge, bleeding-edge, multi-core systems. We're talking about thousands and thousands and thousands of cores. But Amdahl's law says, well, if you're going to run that many cores, you're going to need something parallelizable down to 99.99999999999% parallelizable before it becomes, you know, even profitable to run at that scale. So we got bounds, upper bounds, on just where we should not even bother considering setting n when we have to put together a system. When you go home, when you go to your desert island, build your multi-processor MIPS coconut computer, bear this in mind in terms of how many cores you want to put in it. It has to do with what you're going to do with it. If you're doing something that's incredibly parallelizable, more cores is better, but that limit hits you really fast. And if we study this a little bit more, we can see that, all right, anybody can make positive profit. If I had a one-core machine, I could make positive profit, presumably. If I couldn't, then I'd have to sit back and retool until I could get to at least profitability at one core. What we really want to know is not just, can I make a profit? How does Amdahl guide me towards making the maximum profit? So what we want to look at here is not just if blue is higher than green, if red is higher than green. What we want to look is the difference between blue and green and find where that's at a maximum. You've all done your calculus, so you know finding a maximum is just take a derivative. Blue minus green, well, ddn blue minus green, and find where there's a zero crossing. So if we take the derivatives of all these curves, here we go. First order. The economists in the house are going to call this the marginal cost of another core. And again, thanks to the chronology of our births, we have Amazon, EC2, and a plethora of other web hosting services, cloud computing services that say, if you want one more core, it'll cost you the same amount. You run it for the hour, and if you want 100 of them, it'll cost you 100 times what it would cost you to get one of them. No superlinear scaling in the cost. What we can see is the marginal benefit, the marginal payoff from another core decreases here. This is these diminishing returns that we saw way back in our loop copying example. So you can see here that the cutoffs happen way sooner than you think. If we want D benefit minus cost to be 0, then we want D benefit minus D cost to be equal. So for the orange line, we're going to move up it, starting from one core, move up slowly, slowly, slowly until we're just about to cross over that green point there. Those intersection points tell us the optimal n, given how parallelizable our code is. So under Amdahl's law's assumptions, if we have 50% parallelizable code, I hear it right here. That's really small. That's 4. Anybody could make 4. We could put you in the lab and have you do project 4 on steroids. You could come back with a 4-core system in Logisim for MIPS if we wanted to. 4 is small. 4 is nothing. This is, of course, again, the snobbery of our chronology that I would say 4 is nothing. 4 is amazing to 2001. 4 is nothing to 2011. 4 comes on every rinky-dink EEE PC. I'd be surprised if iPhones start coming with 4. They've got 2 now, right? 4 is coming. There's a lab somewhere in Cupertino that already has an iPhone with 4. 4! What do we bother studying all this parallelization for? We only need it 4 times. And if you look, when we get to 4, that's incredibly close to 1. There's no payoff there. The speed up can only ever get as high as 2. We're so close to the asymptote when we hit these optimums anyways, that when we hit the red asymptote, it's 70% parallelizable. It's 7. That laptop right there, I wouldn't be surprised if that had 8 brains in it. It's already overpowered. We're already paying too much for this muffler. 90%, now we're talking, but we're still only talking 21 cores. That's the optimum. And look at this. This green line here, I just chose arbitrarily. But if that hits a spike, if all of a sudden the cost of the brick goes up, bam. If it goes up from right here to right here, let's say, we go from 21 to 12, even on the 90% parallelizability. So if you are a business-savvy engineer with your startup in the cloud, and you know that today it was quoted at $8 an hour, but tomorrow, maybe it's going to be 9. Maybe they'll pull a little Netflix on you, make it $2 cheaper than you thought it was when you signed up. Well, if those costs go up, the number of optimum cores takes a dive. So this is the dismal science. This is economics. What's interesting, the great insight here is that this continues to hold even if we've got nonlinear curve. If this was not a flat line, but if it was increasing in the number of cores, we do the exact same thing. Just look for this intersection. Find the benefit and find where it intersects at the margin with the cost. To put it another way, look at this curve and find where your benefit curve is tangent to the slope of your cost curve. Basic economics. You guys know how to build a computer. Now you got to know the good way to use a computer. And this is going to involve insights that come from your fundamental understanding of computer science that you bring to the table. You know what it means for code to be parallelizable. You know what it means to fork and then join and to be able to do all of these in parallel. What you're going to have to learn is, okay, it doesn't work forever. This many is too many. This many is actually too many if you're looking to maximize. Parallelization economics rears an ugly, ugly head on all this. Really puts a damper on the parade. So here we go. Let's talk about this for a real algorithm, one that I use every day. Sum of squares. All right, s equals 0. For all of the elements in my array, I'd like to add the square of that element to s. That's 2 instructions per loop. And by the way, it's plus equals, so the value at step k depends on what k minus 1 was doing. K plus 1 depends on k. Everything depends on one step behind, over and over and over again. It's, as written, unparallelizable. P equals 0%. You plug that in, the maximum possible speed up is 1 over 1 minus 0. 1x speed up, max. Doomed. This is MF Doom, Sev Love X. So what we've got here is a bad situation. What we've got here is a bad algorithm. So I opened up the lecture today talking about new and better limits on how good algorithms can get. Let's make another better algorithm. Here we go. This looks pretty familiar. Let's break up that 2 instructional loop and make it 2 1-instruction loops. The first one, we're going to declare a new array, each of which holds the square. Second one is going to do the bad old accumulation over that squared array. And this used to be in Courier, but when I downloaded it, it just came out like this, which is actually super classy if you're used to looking at monospaced fonts, but I apologize if it's a little less than readable, code-wise at least. So, the good idea, break up what used to be 2 instructions in 1 loop, 2 loops, 1 instruction each. We can parallelize this part. Hooray, P just jumped from 0 to 50%. That sounds like a lot until you run Amdahl's law and find out 1 over 1 minus P is 2x speed up, maximum. And that's with a gazillion cores. That's with more cores than Cretius, I guess. Even 2x speed up requiring a gazillion cores and a gazillion dollars means that we're not going to do much better than we could with just 1 core. So that's bad news. If we can't parallelize, if we can't go faster, then I can't make people fall in love by matching up their tweets. My web service suffers for that. Doom. We can go a little faster, but not a lot faster. So here's a smaller doom. So what we got to do is get a better algorithm. Unfortunately, we've been taking 61C, so we remember a couple of lectures ago when we had exactly that. A situation where we can actually build a parallel version of what looked like an unparallelizable block. Plus equals yi means, well, whatever was in the last step, we got to add to it. How do we fix that? use the sum reduction from October 14th, 2011's lecture in 2011, right here. Remember, this date was when you looked back at that date for guidance. Print out both lectures and staple them to your cubicle walls. This algorithm here is one of the most amazing ones I've seen. How close can we get to full parallelizability? Well, if we can build par-accum, this parallel accumulator, which takes in y and the length of y, the closer p can get to 100. So let's take a look at this. This should be sort of familiar to you. So let's imagine we've got n cores on loan from EC2. We've got 100 elements to contend with. So, processor 0, I declare that you shall take 0 through 100 over n minus 1. Take the first fraction, that belongs to you. Those of you who might remember from lab, hey, that's pretty smart because that's chunking. That's going to help reduce the number of cache collisions I have between my multi-threads, which is good. So if we chunk for processor 0, processor 1, and by the way, I'm being loose with the jargon here. It's not necessarily a multi-process thing, but definitely a multi-thread system here. So processor at time 0, processor that we're going to call 1, processing that happens for n minus 1, all gets their own chunks. And each of them, if they want to do accumulation for their share, only has to do 100 divided by n minus 1 sums. And then we can just level them up, level them up, level them up. Everybody kicks up, stores it as an intermediate at some point. And then we have a whole bunch of intermediates here represented by each of these edges that we just have to accumulate again. Now, before we started with 100 inputs, and so we chunked them up. The outputs of this, how many outputs are we going to have? Somebody shout it out. Loudly in one voice. How many outputs do we have coming out of level 1 here? N, which is great because we only have to add them pairwise, which means if we had n cores here, that means we produced n outputs from this level, which means we're finally at a situation where we can completely cover the entire array of inputs at this level of the tree. So we bought n cores from Amazon, and that allowed us to do 100 over n minus 1 instructions to get past level 1. When we kick up to level 2, how long does that take us? Well, because we can parallelize all of these pairwise combinations, it's one instruction. Processor 0 is now able to say, take the result of this guy and this guy, put them together. This input here plus this put here, put them together. It only takes n over 2 of our processes to be active, which if we're running our own system is nice because that's half the power bill again. And then we just kick up. We kick up and up and up and up and up. Whatever n is, we can just build the tree to resolve it until we're out of things to accumulate. And this spans even when n is equal to 1. If n is equal to 1, then we've just got the one process, and it takes the usual worst-case situation. So in total, we're talking about 100 over n, where n is the number of cores, plus log sub 2, n minus 1 minus 2 steps to complete. So if we bring this back to Amdahl's world and think about what this looks like, let's remember one of our nice little assumptions we had was that we can amortize partial quantized instructions over everything. So let's ignore this minus 2 factor. It doesn't really enter in. Let's presume that this actually does hit a nice integer we can reach. What's a few minus 1s between friends? Log, if you remember, is basically counting the number of digits in a number. So 11 has the same number of digits as 12. So log base 2 of n minus 1 is the same as n. If we think about what's happening here, then here is that same bar graph we had before, parallelized. So yellow loop, really, really easy to parallelize. Embarrassingly parallel. Of course, we pay a cost. We're going to have a whole bunch of space in memory, many more memory accesses to make these copies here of y. This is a trade-off you're going to notice a lot if you keep your eyes open. This idea of time versus hardware expense is going to show up. If this exceeds physical memory, then we're going to have to start doing swaps. If the two of them together exceed physical memory, we're either going to have to do some swaps or we're going to have to pay more. Buy more hardware or spend more time. Similarly here, this now can be parallelized, as we saw. And the parallelization is pretty close. If we started with t elements instead of 100 in our array that we wanted to take a sum of squares of, t instructions is what it would take if we had one core. If we parallelize it, the gold bar here, the squaring loop, you can get all the way down to t over n. So arbitrarily large n gives us a sense of how large or how small that bar can get. And similarly, with our accumulation, we've got the t over n problem, but we're also setting us up to have to pay a log 2 cost for the number of cores as well. So much, much smaller, but not exactly as small. So remember, the good news is we're really, really close now to 100% parallelization, if you think about it. Because t over n looks a lot like t over n plus log the number of cores you have. And the number of cores that you have is 8, I think, under Amdahl's law for optimal work. You know, we're talking like double digits, triple digits of cores. So at most, we're tacking on 2. Whereas if t is millions, if we want a million element array that we want to square the sum of, or sum the square of, excuse me, then we're pretty much at the point where both of them are shrinking as n goes up. You know, there is some payback of the parallel accumulator, but because we got smarter about the algorithms, we wound up doing way, way better than we originally thought. We started, big doom. Now we're down to arbitrarily small amounts of doom. We can get this really, really tiny. The smaller it gets, the happier we are. So Amdahl's law applied to this would say, consider now the effects of n on each segment of your code. Some of them are going to shrink as 1 over n. Some of them are going to shrink as 1 over n plus some additional factor. Some of them are going to shrink as maybe even n squared. I don't know. You could imagine a situation like that. Some of them may have communication costs, which wind up giving you square root of n subtraction. But the idea is to imagine in your head, come up with a formula for how fast each part of it shrinks as a function of n, and you can come up with your own little Amdahlian law suited just to your own algorithm that you're implementing. So if you do like Dr. Williams did, come up with a better algorithm or come up with a better guideline to making a better algorithm, you can analyze it this way. You can go back to this chart here, draw your own, figure out what the market is charging you for processing power, come up with the breakpoint, find the optimum, be a big hit at your high school reunions. That's all the money you make. So, quick break there. No EPA today, no peer questioning or anything of the sort. What I do have are these stats that we promised you. So before we go into them, are there any questions about Amdahl's law and the economics of parallelization? Yeah. Nope, just fixing the hair. Okay, cool. And remember, this is all very contingent on you being able to perfectly pass information up this tree, costlessly. So, if you've got a whole bunch of people out there working really hard on implementing these algorithms, but like, ah, man, I'm just getting taken out to the woodshed by these communication costs, maybe you see that as an opportunity. Go, speed this up, make $1 million. The economics are everywhere in this. The slowdowns are what we want to fix. The more we fix them, the better our potential. You know, not just the number of people we can make fall in love based on Twitter compatibility, but also folding genomes, you know, curing cancer, finding links between, folding proteins and finding links between genomes and cancer. Seismic detection for nuclear strikes. And it is very easily parallelizable if you find the right algorithm and if you can implement it on large enough hardware. So here's what's happening when we actually set you folks loose about a month and a half ago on the cloud. You can see that right here, this is me testing it out. This is the Gemini flight, Mercury. Mercury came first? Mercury came first. This is me up in the air, making sure that we can actually go to the cloud and making sure that the PageRank algorithm that we described actually works. And it did, hooray. So then as everyone was struggling to get Hadoop to work locally, and I'm sorry, I shouldn't use struggling, that's a loaded word. As everyone was persevering and enjoying themselves making Hadoop work locally, we launched, we went live right here at midnight. Of course, this is, I think, the East Coast time scale, because where were we operating this? Where were you sending your code when you sent it out to the cloud? Anybody pick up on that? Northern Virginia, home of the greatest minds ever to speak in front of you today during this lecture hour. Northern Virginia. Got a nice little data center out there in the Dulles corridor. And by the way, just to clarify this, you grabbed your code and you put it up in a little bundled packet, wrapped it up in some IP and then some TCP, and then threw it out there. Your code actually flew across America and then lived on those computers in Northern Virginia. And we can see that that first happened with me, Mercury. Here comes Gemini. Our first most intrepid people want to be the early adopters. Grabbed it as soon as we went live. So these timestamps are all Eastern Standard. They grab it, and you can see each particular day, more and more and more. We hit a peak right at the deadline. You could knock me over with a feather. We hit a peak at the deadline of 292 instances running at once. That means, well, let's see, if we were doing six, if we were doing six instances running, what's that, 50 groups? So yeah, about a third of the groups active at once. And we can see that it's always really live right here as people are just banging head to keyboard over and over and over until 3 a.m. hits and then go to sleep. What's neat, what I love most about this graph, at this usage, and what's most applicable to our larger discussion here is, look at that. Troughs, trough, 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 trough. Somebody give me a guess. Nope. I've got access to the raw data on this. That's 1 p.m. That's right now. The only time we could get you people to leave EC2 alone was when we physically made you come to lecture. So what does this mean? What this means is you are the best customers. Because you are, you're in the Western Hemisphere, first of all, which the realities of computing means that's where most of the action is. Silicon Valley especially. America, a broader subset of that. This is just where a lot of the action is in terms of heavy usage of computing. But heavy usage of computing is used heavily to make customers happy. And when are customers happy? When they're using the internet during the daytime, mostly at work. You look at any website, people visit it because they're goofing off at work. So weekdays, middle of the day, specifically around lunch breaks, specifically when we made you sit right here and leave those poor computers alone. Look, you're just abusing them at this point. That hurts. Which means that, for the savvy engineer out there, oh, well maybe if we redid this project, we should take it away from the flat fee and put it on the spot market. So if we reran this again, maybe we'd give you bonuses not just for speed up, we'd also see if you could bring it in under budget. See if you can find a way to, we know that nobody's using the computers at night, which should mean I should be able to get it at a discount at night. And since you guys are just perfect night owls anyways, I don't see that that's too onerous. And if you do like getting your beauty sleep, cron jobs. So this is what you guys looked like for a week. Total cost just on this right here, $2,400. And we incurred about $10 more just on paying to move data back and forth from S3 and to download from that. And also there were a couple of wiseacres out there who decided it'd be fun to use our C1X large instances, which run you about $1 an hour. So they're not included on this chart, but there was a blip right here, and then right here, and then I changed the password. So mean usage, 81 cores at a time. Median usage, just for that main hump there, I cut off the outliers, 52. So this is what you guys looked like. So that was project 2. And next lecture, bringing it on home, we'll let you know how everything went similarly with your stats on project 3. So economics and parallelization, thank you very much. And I'll see you guys office hours. We are holding office hours during Dead Week, so I will at least be there. Our TAs might be struggling with final exams, but I'll be wide open. So.